so today we're going to discuss our next topic, that is the strain. So let's say strain or the epsilon. So basically we have the equivalent of strain is the ratio of the deformation over the length. So basically we have lowercase delta. This is equal to the deformation. So if you say deformation, it can be an elongation or a shortening. So for example, we have a material or a structural member, for example, that is to carry a compressive force P. Okay, so compressive force will result to shortening. So we use the negative sign for shortening as our sign convention. So on the other hand, for example, we have a material or a structural member that is to carry a tensile force. So tensile force will cause a positive deformation, or basically that is elongation. From the Hooke's law, as per described by the Hooke's law up to the point of the proportional limit, that is, we have stress is directly proportional to the strain. Okay, that is on up to the proportional limit from the Hooke's law. So we have, for us to have an equation, the stress is equal to, we are to introduce a proportionality constant multiplied by the strain. So wherein the equivalent of this proportionality constant is basically equal to the E, or this is the modulus of elasticity. So we have our proportionality constant, that is basically equal to E, or the modulus of elasticity. So the modulus of elasticity of any material can be determined using our laboratory apparatus, or the UTM, in a laboratory experiment. So if we are to recall, what's the equivalent of sigma, or the stress? That is the force divided by the area. What's the equivalent of the strain? That is the delta deformation divided by the original length. So for example, if we are to compute for the deformation, from this equation, we have sigma is now equal to proportionality constant is the modulus of elasticity multiplied by the strain. So stress is basically force divided by area equal to the modulus of elasticity. Strain is the ratio of the deformation to the original length of a given sample. So computing for the actual deformation, this is delta equal to the applied force, the length divided by the cross-sectional area times the modulus of elasticity. So this is for the deformation, or that is for the actual deformation. If we say actual deformation, we assume that the applied force P will be equally distributed to the cross-sectional area of a given material, or a given structural member, or a given sample. So let's have an example. So let's have this example. So for example, we have this shaft acted by multiple forces. We have at point A, there is 2,000 pounds to the left. At C, we have 6,000 pounds to the right. And at D, 4,000 pounds to the left. We have two diameters for segment AB, 0.5 inch. Then for segment BC and CD, we have a constant diameter of 0.75. The property of the material, this is for steel, that is, the modulus of elasticity is equal to 29 times 10 raised to 6 pounds per square inch. So we are required to compute for the total deformation. So basically we have the equivalent of the total deformation will be the deformation for segment AB plus the deformation for segment BC plus the deformation for segment CD. It's just for this example, we are using again the load diagram to determine the actual force per segment. So we are using the load diagram to determine the actual force per segment and to determine which segment is under compression or under tension. Okay, for the load diagram, We usually start on the right end. We are assuming forces to the left to be negative and forces to the right to be positive. So we have at point D, we have 4,000 pounds. The effect of this 4,000 pounds to the member is compression, and it is to the left. So we assume this to be negative. So this is negative 4,000 up to point C. At point C, we have a force to the right that is 6,000 pounds. So we do the summation. Positive 6,000 plus negative 4,000, that will give us a value for segment BC, a net force of 2,000 pounds. Then as you can see, we don't have a force at point B, so which means the 2,000 pounds will be extended up to point A. So this is also equal to 2,000 pounds. At point A, we have an applied force of 2,000 pounds to the left. We are assuming to the left forces to be negative. So this is negative 2,000 plus 2,000, that will give us a value of 0, which means this shaft is under equilibrium. One advantage of load diagram, we can determine which segment is under compression and under tension. So for the negative segments, this is under compression for segment CD. Segment BC is under tension, and segment AB is also under tension. So we have the axial force for member or segment AB is equal to positive 2,000 pounds. Then for segment BC, the axial force is also equal to, for segment BC is also equal to 2,000 pounds, positive since under tension. And for the last segment, this is the last segment CD, under compression, we have negative 4,000 pounds. So how do we compute for the total deformation? Basically, deformation is the axial force, the length, divided by the area, times the modulus of elasticity. So computing for the total deformation, that is equal to, let's have segment AB. Axial force segment AB is positive 2,000 pounds. What is the length for segment AB? We have this is 5 feet. This is 5 feet. We need this one in inches. So this is multiplied by 12 inches is to 1 foot. This is divided by what is the cross-sectional area of segment AB. We have a diameter of 0.5 inch. So this is 0.5 inch squared by 0.5 squared by, this is divided by 4. This will give us a unit of square inches. Multiplied by the modulus of elasticity, this is equal to 29 times 10 raised to 6. That is pounds per square inch. Okay, if we are to do unit analysis, we will cancel pounds, then inches squared or square inches. This is feet. The remaining unit will be in terms of the inches. We are to do the same for segment ABC. For segment BC, the axial force is equal to 2,000 pounds. The length of segment BC is equal to 4 feet. To be multiplied by 12 inches is to 1 foot. And this is divided by the area this time. We have a diameter of 0.75 squared by divided by 4. Then multiplied by the modulus of elasticity. This is 29 times 10 raised to 6. Okay, then plus our last segment, the only segment under compression. The axial force is equal to negative 4,000 multiplied by the length, that is 4 feet, multiplied by 12 inches is to 1 foot, to be in inches, divided by the same area, we have 0.75 squared by, this is divided by 4. Then the modulus of elasticity, 29 times 10 raised to 29 times 10 raised to 6. All we have to do is compute for the summation. This will give us the total deformation of the segment, or the total deformation of this segments. So it's the same as 2,000. We can factor out Okay, modulus of elasticity, since we have a common material for all of the segments. That is 2000 times 5 times 12. This is divided by 0.5 squared of pi divided by 4. Then plus for segment BC, we have 2000. The length is 4 feet this time. Multiplied by 12 to be in inches. The diameter is 0.75. So 0.75 squared pi divided by 4. Then minus, we have 4,000. The length of that segment is 4 feet multiplied by 12. The area is, we have 0.75 squared pi divided by 4. Okay, so we don't have enough memory for our calculator. So I'll just be doing the first two. Then minus 4,000 multiplied by 12, multiplied by 4 feet times 12 is to 1 foot divided by 0.75 squared pi divided by 4. And then divided by the modulus of elasticity, 29 times 10 raised to 6. So we have the deformation is now equal to 0.01358 inch. And as you can see, this is positive, which means we have more elongations compared to the compression. As you can see, we have two segments are under tension and one segment under compression. So the positive sign means this is elongation. So this will be our solution.